Okay, so what we were saying about the autocorrelation, what you see here, actually, this is if you see the time and delay. So in general, I mean the in time domain, the Gaussian shape is like this, okay? And in case of autocorrelation, uh, shape is like this, but this plot is delay versus intensity, okay? So this is the formula and autocorrelation and is equal to the, because shape is Gaussian, so 1.41. Okay, so, and this one is full width half maximum of this plot. Full width half maximum of this one multiply 1.41, so it will give you the value of the time here, delay time, and that would be uh, the pulse duration of the pulse. And if you consider this pulse shape, it will be like this, and the autocorrelation signals will be like this. And in this case, you multiply 1.54 with the full width half maximum of uh, this curve. Okay, and mostly we apply this fitting, this one. According to the scientists, this shape is more realistic than this one for the lasers. Okay, so we always apply this one. So when we plot, take the full width half maximum and we multiply with this factor, and this will give the value of the pulse duration. Okay, so this is the autocorrelation. And how it works actually, what you do, let me go back a bit. This is your setup. Okay, so from here we take the voltage values. Okay, and from here we take the time values, and what we do here, these time delay values we plot on this side. Okay, and this voltage is directly proportional to the intensity, and that we plot here. So here is the intensity, there is a time delay, this value, whatever you, and that tau is equal to 2L over C. So we move this translation stage a bit and we calculate this value, and then again move and calculate, and then again move and calculate, and we write all these values here, okay, in small steps, and we make the measurement for each value, what intensity or what is the voltage output, what intensity that could be, okay, and then plot is drawn according to that one, okay, and then we take the full width half maximum. Then we take the full width half maximum here, and okay, full width half maximum. Okay, so multiply this one with 5.14, and that will be the value of your pulse duration. In time it will be definitely, because this is the time scale. Okay, this is how it is done in actual measurement. Okay, so after making this setup, you take the reading for the small changes and make some measurement about the intensity or the voltage level to what, I mean, this detector will be connected to somewhere. It can be oscilloscope or can be something else. Then you can use that value on the y-axis and the time value on the x-axis. And the plot will be drawn like this. At certain point, there will be a maximum intensity. At this point is lower intensity. Then again, the intensity will start falling with the passage of with the delay. Okay. So then you can calculate this full width half maximum and multiply this one with 1.54, the factor, and that would give you uh, the the pulse duration of the laser. Okay, this is the autocorrelation, which is the simplest technique. But this autocorrelation is not providing you the necessary information. It only gives you the value of pulse duration, and that pulse duration may have some plus minus error in this case. But the more sophisticated the technique, which is called the FROG, frequency resolved optical gating. I will not go in much detail of this FROG because this is a high level kind of things you people may not understand that much, and you people don't need it for this the course. But I give you a little bit idea about, like, only the all the arrangement is same, the setup is same. In place of photodetector, we use the spectrometer. And for each delay value, we take the spectrum. For each and every delay value, we take the spectrum. Okay. And that spectrum actually, we make like a matrix. Okay. So there is one value, which is the wavelength, which is same, and the different intensity values from the spectrometers. So we have different plots. And that plot will be in the form of matrix. And then this matrix data is used for certain kind of retrieval software. And that retrieval software retrieve the some information which we cannot get from the autocorrelation. And that is the phase values, pulse duration. I mean, if the pulse is like have some problem, there is a tilt, etc., etc. Okay. So the mathematical formula for the frog is this one. This is your frequency. This is your time. Okay. Delay time. And it's integral. This is electric field, the actual signal. And you have this overall equation, which is the wave equation actually. And you have this one time delay. As I mentioned that I will not go in much detail because there are so many things in this one. The main theme actually is here that in place of detector, we use the spectrometer and we take the spectrum for each and every delay, and then we'll make the matrix. And that matrix is used uh, with a different kind of software. We call it frog software, and that frog software will give the information that is about the phase, pulse duration, etc., etc. And when we make a matrix, uh, when we make the matrix actually, from this matrix, we get this kind of, it's called interferogram, it's images. Okay. If you have a matrix, what is matrix? The values here and some values here, 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 here. And that can be 200, 300, or 1,000 values. Okay. So column and the rows. Okay. That may be a like 200 by 200 or 300 by 300. Okay. So even you can see in the origin as well. So this matrix is converted into the image and we can see image like this. Okay. And these images will give you the information that if the pulse is chirped, if the pulse is unchirped or pulse is chirped, is positively chirped or negatively chirped. You can see the difference. If it is unchirped, it's very nice round shape. If it is chirped, then you have like this kind of the shapes. So from the matrix, how did matrix we make that we take the data for each and every time delay in the form of a spectrum. And that spectrum, like if you take 100 data sets, and then there will be 100 spectrums, and you make a matrix, and then matrix is converted to the image, which we call the interferogram in case of frog. And that images are like this. Okay. And these images are giving you the information. And from these images, you can also get some other information as well. What I skip here, because in case of frog, we always need that spectrometer. So what exactly spectrometer is? Spectrometer take the light pulse and we use the grating to disperse it and then the detector to detect it. Okay, like here, pulse is entering, very small slit. Okay, and we have here the collimating mirrors, curved mirrors. Okay, so these curved mirrors, like light is entering from here, light definitely it will spread. It fall on this collimator mirror, then it will go to the grating, and from grating to the other collimator mirror, and then from here to go to the detector where we can see the spectrum like this. Okay, so it's disperse the light, and this dispersion actually it helps us to see the spectrum of the beam which is entering the spectrometer. Okay, so why it's necessary to show a little bit about the spectrometer, because the spectrometer is used in the frog setup, in this setup. So if you animate this the spectrometer, there are two kind of spectrometers. In this one here, we use the reflecting type grating. And here in this one, we use the uh, reflection grating, but it's not a reflecting type, it's a transmission type. So light is passing through. When the light passes through, it disperses. Okay. And then it moves towards the detector, sorry. So here, when the light here, and this is a curved mirror, and then it go to the grating, and then here and here. After the grating, it disperses, and this dispersion, you can see the spread of the light, and it falls on the detector, but we can see the spectrum here. And here the same thing, only we are using the transmission type grating. And what are the grating? The grating is a very sophisticated kind of things. Number of rulings on it, like thousands. And that is why the light is dispersed from these lines on this grating. This is the same thing which I explained already. When the two uh, electric field, delayed electric field and the actual electric field, they overlap temporarily, then we get the signal. Okay, and that signal is similar like in case of frog or in case of autocorrelator. Only difference is that in case of frog, we detect this signal with the help of the spectrometer, but in case of autocorrelator, we detect this signal just with a simple photodiode. This is, I explained again. So here, this animation, you can see this is, if you remember the grating stretcher, compressor. So how the compressor is optimized, and this is the image from the frog. Okay, the matrix data, how it changes with the separation of the, if we change the separation of the grating in case of stretcher. You can see here. So the separation is decreasing, and you can see the difference in the shape. So from here, we can guess at which value of the grating separation, the image is much more smoother and kind of unchirped or something like this. Here you can see again. So that is why we use the frog for optimization of the whole system. Okay, because the grating compressor is one of the important thing. Whether you can optimize the grating compressor or you can optimize the grating stretch, it depends. Usually we use the grating compressor to optimize the system. Optimize mean to adjust to the minimum possible pulse duration. Now the applications, actually last few slides, there are so many applications. Okay, I don't go in detail of that applications. Uh, you have we can generate the coherent X-rays, and this is very common practice in these days. We use when you use the femtosecond ultrafast lasers. Okay, and we can generate the plasma, and then we can study the laser and plasma interaction, and we can use this one in eye surgery. We can use in microfabrication, machining, and chemistry, chemical reactions. What is a chemical reaction to generate the terahertz radiations, and in medicines for the cutting, for the eye operation, and in industry for many other things. So the eye surgery, actually, um, femtosecond laser especially is used, not the picosecond laser, because picosecond laser can heat up and damage the other part of the eyes. So mostly we use the femtosecond here. You can see in these figures with the help of femtosecond laser here, the flap of your eye is lifting up. Here you can see, here you can see. And this precise kind of this precision can only possible with the femtosecond laser. Okay. And why it is like this, you can see, I wrote down here that femtosecond laser, actually, because it's a very short pulse. And so the short pulse mean it can work in a short time, and less heat is generated as compared to the picosecond. Picosecond take a longer time, so the heat spread around. It may damage the tissues around. But in case of femtosecond laser, it's not like this. That is why it's much safer. And so it's without burning or tearing the tissues, okay, because of very short pulse, okay. And also in case of longer pulse, as I mentioned, that heat spread. Pulse is long, heat spread, okay, and it damage the issue. So that is why picosecond, even you cannot use a femtosecond. It's more a reliable kind of thing for the laser surgery and the LASIK. What is LASIK can come in the next slide, okay? And so laser assisted in situ keratomyelitis. So the correct your vision somehow, the focusing, okay? So this is the setup, which is it's not easy to understand because there are many things actually with this setup. The main thing is that to understand uh, that in this kind of technique, which is called LASIK, they correct the your can correct your eyesight. So glasses can be removed, and there are many cases now in these days. People they have this treatment, and their eyesight is much better. The focusing is adjusted. How it is, you can see here in this animation. Probably it's just a rough animation when you shine the laser so that the cornea actually is reshaped with the laser pulses. Okay, so cornea is reshaped. So if the cornea is reshaped, you can see the focus here, it exactly at the retina. We wear the glasses if the focus is here somewhere, and if it is on the retina, we don't need to wear the glasses. Other application is laser-driven electron acceleration. And that acceleration actually is very promising. Rather than to use the huge accelerators, magnetic field and this and that, electric field. you need to make hundreds of meters or something like this. So the laser, with the help of laser, you can do it on the very small scale. And these electrons are not generated directly, but we use some certain kind of gas jet, very small kind of jet, and the gas is filled in it, mostly inert gas, helium or neon, and the laser is made to fall on it. And after this here, like this is a gas jet. Okay. And the laser is supposed to fall on it, focus on it. Okay. And then on the other side, you can see the bunch of electrons. Okay. And that electrons are supposed to be directed somewhere. That is a different arrangement. So with the help of this laser, we can generate the electrons and it can be directed for different applications. These electrons, bunch of electrons can be used. And from these electrons, we can also generate some other atomic particles as well. But that is long story. And here I'm just giving you the little overview about what can be done with this femtosecond laser. So you can see here, this is from here, and you can see these accelerated electrons can be seen. And many people are doing this kind of work in these days, actually, in the many labs, actually. This is one of the hot topic to generate the atomic particles by using the laser, especially ultrafast laser. Drilling and machining is much more convenient, actually, with the femtosecond laser. Even though picosecond is also in ultra-fast category, but the femtosecond is because of the much shorter in pulse as compared to the picosecond. So that is why it's compared here, and it has much more finer, you can say, the drilling here as compared to this picosecond. And this one, you can see the engraving. Okay. So because of extra heat of these pulses, picosecond pulses, the hole is not very fine. And you can see the other part of there are these parts which are not needed if you make it not a clean hole, actually. So here it's much more cleaner. Here you can see in case of if you animate, actually, the picosecond and femtosecond is much more cleaner. And because of the extra heat, because the pulse is very long, so it generates the heat around it. So the hole is not very clean, especially when you need really precision. So you cannot use a picosecond laser for drilling purposes. And at the last, actually, is terramobile laser. Terramobile laser, why it's necessary to show in one of the applications. This is a same category of femtosecond lasers. It has a concept of lidar. We can use lidar. We can detect the aerosols, the particles in the air with the help of this one. And we can also use for the remote ignition. And we can also use to direct the lightning from the sky to on the earth by using this technique. So here, actually, you can see here, these all are different parts of the laser system: oscillator, stretcher, amplifiers, and compressor, everything are there. And it's called terramobile because it's in the kind of big container, and you can move it. You can, I mean, wherever you need to do some certain kind of experiment, and the filament is generated. Very high power filament. Filament means that uh, when the very high intensity or very intense laser pass through the air, some kind of ionization happened. And we see that in this kind of filamentation. It's filament, like filament of the bulb or something like this. So that filament is like very hundreds of meters. We can see if the laser is very intense and it's like in joules, hundreds of joules maybe, then you can see that filament here like this here in the air. Okay. And this filament actually, this it can be used for different applications. I mean, it can be used to attract the lightning from the sky, and it can be used to um, ignite something from far or something like this, or as a weapon, you can say as a weapon. So, and it also help you to direct the light from the sky to place where you want to fall it. So it can be used as a tactical weapon actually. How it can be like this, you can see if it is as a lidar to detect uh, something from the sky, and the reflection or the deflection of the laser from the particle I mean, you can detect it. And that will give you the information what kind of clouds are there, what kind of particles in the atmosphere, or something. It's called remote sensing as well, using a laser. And for this kind of thing, you need a terawatt uh, laser, definitely. Not a petawatt, because petawatt cannot come in the container, maybe, but the terawatt laser. So these are the major applications. And the course is concluded. Okay. And the lecture messed up because of this technical problems, but anyway, it's concluded. So I don't know you people, if you people are feeling sleepy or something like this.
No, sir.
No, sir,
Okay.
we are fine. I'm
Okay.
fine.
Yeah. So if you have a question now, or if you want question in the last lecture mean is just evaluation of you people. And so, but if you have now, you can also ask if you have anything in your mind. It's not easy to understand, frankly speaking, for you people, background wise. But if you try a little bit, maybe you can. Maybe some of the people they understand a bit more. Gazanfar, he left.
Yes, sir.
You must be sleeping now because. So, what do you think, Gazanfar? Now you understand that
Sir, last
autocorrelation.
part, sir, yes, I understand. But the last part of video of this lecture, where we discuss the applications, are little bit conceptual, and I
Yeah, I
didn't get
mean,
much of that.
yes, I mean, application. I want to give a little hint about it. It's not my intention to explain because this one is separate course. I mean, the application of the ultrafast lasers. Okay, and each and
Okay,
every application has a like you need to dig out. It's huge things, and people are researching on these things. Okay, so you
sir, I
cannot.
have
Yeah,
yes, yes, sir. I have one question. It's not one question, it's just the confirmation. Sir, as you mentioned in the when you're discussing about applications, especially the eye surgery, we prefer the femtosecond
hmm
laser
hmm
than the
hmm
picosecond.
hmm
It's just because of the energy.
Not energy.
Picosecond have the
What do you mean energy?
uh, peak power.
Not the peak power actually. It's pulse duration.
Okay.
Pulse duration is important here.
Yes, because the area under the pulse will be gives the average energy, I think, number of the photons.
hmm
So
So
the small femtosecond has the small pulse duration, so means the number of photons will be less than the picosecond.
number of photon will be less. No, correct your understanding.
The area under the spectrum is gives the energy, I think.
No. No, that is radiance. That is irradiance you are saying about. That is irradiance.
Okay.
Okay, so correct it. Maybe next time we can discuss. Okay, so any other who is not sleeping now or who is still there?
Sir, I have a little question.
But you are missing your
Sir, I
wedding
have,
ceremony. Yeah, you are still here.
yes, sir, when it is not something very, very important,
Mhm.
then I miss. And to be honest, I don't
Okay,
like a wedding ceremony.
okay, go ahead.
Sir, can you move to the image of being splitter?
Image of the beam splitter. What do you mean?
Slide backward, little back. Just this one, this one,
Which one?
this one. This previous, this
Hmm.
one is good.
Okay. Hmm.
Sir, we can see uh, there are two rays splitted. One is delayed and one is fundamental.
Mhm.
There is a point where these two could interact.
Mhm.
If you could see, sir, don't their interaction won't affect each other.
No, this is the characteristic of the crystal. They're supposed to overlap there each other. I mean, interaction.
Sir,
We actually the thing is that we attenuate. Attenuate means we reduce the intensity of the beam when it enters.
sir, I'm talking about the point exactly below the beam splitter.
That no. This is just in the diagram. Height is different.
All right.
This height is different actually. This is because I'm not showing you a 3D diagram. This is a 2D diagram, so that is why.
Yes,
But even in this case, they can cross each other. It doesn't affect. If you have a
yes,
clean room, if there is no dust particles.
yes, yes.
Hmm. Okay, so Salman must have so many questions, isn't it?
Sir, I also have another question.
Okay, go ahead.
Sir, why we use electron accelerator?
To use, there are many applications of the electrons for certain kind of things. We accelerate the electrons, and then we study many other things. You know that a free electron laser also exists.
Yes,
And
sir.
we need the
I
electron to generate the X-ray as well. So there are many
yes, sir.
applications. Yeah.
Yes,
Okay, so Mauricio, are you there?
Yes, I'm here.
Okay, so today was the last lecture. So in the next lecture, there will be a kind of evaluation. Evaluation
Mm,
means, I mean, I want to evaluate you people, how much you people understand or
yes,
whatever.
sounds good.
Yeah. So I'm assuming you will be there.
Yes,
Uh,
yes, for sure.
yeah. So probably you can also ask the questions if you have on that day,
Um,
or maybe today if you want to ask anything.
um, okay. Well, I don't have a question
Hmm.
for today,
Hmm.
but I just want to thank you, no,
Hmm.
for your dedication and time for you give to this course.
No, you're welcome. Actually, at least you people. I hope you people could understand something. And so I think Salman is not here. So Tahura and Arusa Hadi, you people are there or left?
Yes, sir.
So did you understand? I mean, something in today's lecture or like?
Yes, sir. It was interesting,
Hmm.
especially discussing the application.
Hmm.
I like it very much.
Hmm. Application
Uh,
side.
it is used in many applications such
Hmm.
as eye operation that you
Hmm.
discussed in detail.
Hmm. Hmm.
And thank you so much for giving us time and delivering your lectures.
You're welcome. You're welcome. So only intention is to you people to learn something.
Thank you so
So
much.
yeah. So the Ehtisham, you are there or you are also not there?
Yes, sir, I'm here, sir.
So
Sir,
yeah.
sir, actually, I was confused about the after the autocorrelation, we see only two beams coming out of the crystal, but in the spectrum we see three. I mean, the second
Because this is a
harmonic
cross. There
beam.
is a cross. So two beams having the same wavelength. This is a crossing. This is a crossing here. So the center one is green one, which is the half of the actual one. These two are out because they are crossing each other.
Okay, thank you.
That is why there are two beams. Okay. So David.
Yes, sir.
So probably, I mean, if you have any question, you can ask. Otherwise, we finish.
Yeah, it's very interesting the last application. I go good in deep in detail.
Yeah, you
It's
can dig it out.
okay.
Yeah. Amna Said.
No, sir, I have no questions. And sir, thank you so much for this course. I
You're
was a
welcome.
beginner and I learned a lot about ultrafast laser.
Yeah, sure. I mean, I hope you people learn something. So probably, but the next, I expect you people to come in the next one.
Yes, sir.
Okay. And Nargas, Ghafoor, you are
Yes,
there?
sir. Yes, sir, I'm here. So thank you for this course. It was really helpful, and today actually now I can picture the. Basically, I studied autocorrelator and I was just digging in mathematical terms. Now I can get a picture of it.
Yeah, it's good
What
actually.
it is and how it is in terms of spectrum, and plus the last part, it was very interesting. I am from since the very beginning of the course I studied about the LASIK, and I even mentioned in my first assignment that was the application I was very wondered of. So thank you for this course.
You're welcome. You're welcome. Okay, so Salman, are you there?
Yes, sir.
Before you were sleeping?
Hello, sir.
I think I asked you many times, but you are not replying.
Maybe, sir.
Okay, I think you are sleeping. So we conclude here. So let's meet next Sunday and try to go through all the slides before to enter in the class. Okay.
Okay, sir.
Okay, so all of you, there are few actually missing today, but I expect all of you to come in the last one and you people to be evaluated in somehow in some matters, and you people will also get some not in the next class, but later on I will send you the kind of certificates or letters or whatever, whoever finished it. I have to check some of the assignment yet, but in any case, we will meet in the coming Sunday. Okay, so thank you very much for attending this class, and we'll meet in the next class. Okay. So meanwhile, take care. Good night and Allah Hafiz.
Officer.
Allah Hafiz. Bye bye.
Officer.
Okay, sir. Allah Hafiz. Good night. Allah Hafiz.
Thank you very much, sir.
You're welcome.
Allah Hafiz, sir.